so now in this class we are discussing about the power system architecture. Okay, so third unit, so that is nothing but transmission line parameters. So in previous class we are discussing about, so for transmission line use which type of conductors. First of all, what is the conductors, okay, and which materials are used for the conductor, okay, and that conductor properties both are discussed in previous class. Okay, so now in this class we can discussing about transmission line parameters. Okay, see. Okay, see transmission line parameters. See here, the transmission line has mainly 4 parameters. Okay, so what are those? Nothing but resistance, inductance, capacitance, shunt conductance. Okay, so any transmission line having mainly these 4 parameters, those are resistance, inductance and capacitance and shunt conductance. These parameters are uniformly distributed along the line. Okay, so see, hence it is called distributed parameter of the transmission line. See here, you have to see in this diagram, see, these are, so capacitance, conductance, resistance, inductance. Okay, so this is the transmission line model. So in this you have to explain these parameters are uniformly distributed. Okay, see here, you have to take how many capacitors? Same as inductor, resistance and conductance. Okay, so that's why this is, hence it is also called the distributed parameter of the transmission line. Okay, this is also called distributed parameter of the transmission line. See here, the inductance and resistance form series impedance. So what is the transmission line? You have to, so the transmission line having, any transmission line having 4 parameters. What are those? Resistance, inductance, okay, conductance and capacitance. Here, the inductance and resistance form series impedance. Impedance, okay, the combination of the inductance and resistance forms the impedance, but Z equal to R plus J omega L. Okay, so whereas the capacitance and conductance form the shunt admittance. These two will form the admittance Y equal to G plus J omega C. So here G means conductance, C means capacitance. Okay. So see here, the performance of the transmission line depends on the parameters of the line. So you can take any transmission line. Okay, so that transmission line performance will be depending upon these parameters of the line. Okay. So first you have to discussing about resistance. Okay, so all of you well know about resistance. Okay, so what is the resistance? Resistance is nothing but resistance is the opposition of line conductors to current flow. So that means, so the parameter which opposes the current flow, that is nothing but the resistance. Okay, see calculation of resistance for solid conductors. So in previous class we are discussing about this type of conductors. What are the type of conductors? Solid conductors, halo conductors, okay, composite conductors like this, and bundle conductors. So here the resistance of the transmission line conductors, okay, is so here you have to first calculate for the solid conductor. So the solid conductor is a single strand of conductor. Okay, see here the resistance of the transmission line can be expressed as R equal to rho L by A. Okay, so what is the formula? R equal to rho L by A. Here rho is nothing but resistivity. Okay, resistivity of the transmission line. Okay, so L means inductance and A means area of cross section of the wire. See here where R is the resistance of the line conductor and which will depend upon which parameters here? Resistivity, length. Okay, here L means length, A means area of cross section of the line conductor. Okay, see here these factors must be taken into account while calculating the resistance of overhead line conductors due to the relations among them. So whenever you have to find out the overhead transmission line resistance, at the time these parameters you have to must taken into account. So those are resistivity, length, area. Okay, so the transmission line resistance for the solid conductors is given by R equal to rho L by A. See from equation 1 you can observe that here R is proportional to L. Okay, that means the resistivity is proportional to the length. That means when the length of the conductor will be increases, the resistance of a line conductor can also be increases. Why? Because these two are proportionality constant. Similarly, R is also proportional to rho. So that means resistivity. Okay, here the resistance is proportional to the resistivity. That is when resistivity of the material. Okay, so whenever you have to use the material for line conductor, so whenever the resistivity of that material will be increases, okay, so at that time the resistance of the line conductor will be more. Okay, similarly here R is proportional to 1 by A. So that means it is inversely proportional to the area of cross section of the conductor. Okay, see, that means when the cross sectional area of the line conductor can increases, so at that time the resistance of the line conductor will decreases inversely. Okay, so these are the relations among the resistance. Compulsory, there will be a temperature. Okay, the temperature will affect the resistance of the transmission line conductor. How the temperature will affect the resistance of the transmission line conductor? Now here you have to see. See here the variation of resistance of metallic or solid conductors. Okay, so the resistance of metallic or solid conductors with temperatures is practically linear. Okay, so that means so linear relationship between the resistance of the metallic or solid conductors with temperature. See, hence this factor can be also taken into while calculating the resistance of the overhead line conductors and the charge of resistance of the line conductor. See, whenever we have to find out the resistance of the transmission lines, so at the time must and should we have to take the temperature is also in consideration. Why? According to the temperature changes, the resistance will be also changed. Okay, see here, suppose R1 and R2 are the resistance of the conductors at T1 degree centigrade and T2 degree centigrade respectively. So if suppose T1 degree centigrade, okay, if you first you have to take the T1 degree centigrade, that is the one temperature. If you have to take the T2 degree centigrade, that is the another temperature. At both temperatures, so T1 at T1 degree centigrade, R1 is one value, and at T2 degree centigrade, R2 is some particular value. So when you have to take in T1 and T2, okay, so that means in different temperatures the resistance will be also different. So that's why you have to take the R1 and R2. If suppose when T2 greater than T1, okay, so that means the temperature T2 will be greater than T1 if alpha 1 is a temperature coefficient at T1 degree centigrade. Here you can assume the temperature coefficient is alpha 1 for T1 degree centigrade. Then the resistance of the transmission line conductor can be also expressed as, okay, so R2 is equal to R1 of 1 plus alpha 1 into T2 minus T1. Okay, so here similarly alpha 1, how you can find out the alpha 1 is equal to alpha naught by 1 plus alpha naught T1. So alpha naught is nothing but temperature coefficient at 0 degree centigrade. Okay, at 0 degree centigrade you have to take the temperature coefficient will be alpha naught. Okay, so skin effect and proximity effects also considerable factors while calculating the resistance of overhead line conductors when the transmitted power is AC. Whenever you have to transmit, so you have to powers are AC power and DC power. If suppose by using the overhead line conductors, we have to transmit the AC power. Okay, so whenever you have to transmit the AC power, at the time skin effect and proximity effects are also considerable factors while calculating the resistance of the overhead transmission lines. See, skin effect. So what is the skin effect means? See, the tendency of alternating current to the concentrate near the surface of a conductor, okay, is known as skin effect. Okay, the tendency of alternating current. Okay, so the alternating current which is near current to concentrate near to the surface of a conductor is known as the skin effect. Okay, so this is the current flows over the surface. Here there will be a no current. So that means the total entire current will goes to the near the surface. So at the time there will be no current inside the transmission line. So that's why at the time it may be cause a one effect. That effect will be called as the skin effect. See here, due to skin effect, the effective area of cross section of the conductor through which current flows is reduced. Okay. So whenever the skin effect will be occurs in the transmission lines, at that time the current flow will be reduced. Okay. See here, the resistance of the conductor is slightly increased when carrying the alternating current. So whenever the transmission lines will carrying the alternating current, so at that time the resistance of the conductor will be also increases the It's like, see, the resistance of the conductor is slightly increased when carrying an alternating current. So whenever it carries the alternating current, so at the time the resistance of the conductor will be increases. Okay. So what are the factors? Okay. Now we have to see the what are the factors affecting on skin effect. Okay. So now you have to see what are the factors affecting the skin effect. Means see here the following factors are affecting the skin effect. What are those? Frequency, diameter, shape of the conductor, and type of material. So first of all, frequency. Whenever frequency will be increases, the skin effect will be also increases. Okay, here see, skin effect increases with the increase in frequency. Okay, here the skin effect will be increases with increase in frequency. Next one is what? Diameter. It increases with the increase in diameter of the conductor. Okay, so the skin effect will be also increases by increase in the diameter of the conductor. Okay, next one is what? The shape of the conductor. Skin effect is more in solid conductor and less in the standard conductor. Okay. Skin effect value will be more in the solid conductor, but it is less in standard conductor because the surface area of the solid conductor is more. Okay. Why? Because the surface area, whenever the surface area will be more, so at that time the skin effect will be also more. That's why here in the solid conductors, the skin effect is more compared to the standard conductors. Type of material. Skin effect increases with the increasing permeability of the material. Different materials having different permeabilities. So whenever the permeability value will be increases, so at that material at that time the skin effect will be also increases. See, due to skin effect, the resistance of the conductor can be calculated with the following relation. See, RAC equal to 1.66 into RDC. Okay, so RDC means that is the resistance of the DC transmission line. RAC equal to 1.66. RAC is nothing but resistance of the AC transmission line. Why you can get this formula is, see here, in a single phase or two-wire DC line, the total resistance known as loop resistance is equal to the double resistance of the either conductor. Suppose if you have to take the single phase or two-wire DC line, the total resistance known as the loop resistance and is equal to the double resistance of the either conductor. Okay, that resistance is a double value. In case of three-phase transmission line, the resistance per phase is the resistance of the one conductor. So what is it? So in three-phase, we have in the three phases. Okay, so at that time, three-phase, the resistance per phase is the resistance of the, what is the resistance of the conductor we have to take in, that is equal to per phase resistance. Okay, so next one is what? Proximity effect. See, what is the proximity effect means? When the conductor carry the high alternating voltage. Okay, so whenever the conductor will carry high alternating voltage, then the currents are non-uniformly distributed on the cross-section area of the conductor. Okay, so you have to transmit the high voltages. So at the time when the conductors carries the high alternating voltage, then the currents are uniformly. Okay, so at the time the currents are non-uniformly. Sorry, at the time the conductors are non-uniformly distributed on the cross-section area of the conductor. Okay, so that's why whenever that effect will be occurs, that is called the proximity effect. See here, direction of the current. So without proximity effect, so current direction will be same. Okay, but whenever you have to take in the proximity effect, so at that time the current will flows in the opposite direction. Okay, so see here, okay. See here, if the conductor carries the current in the same direction, then the current is crowded in the remote half portion of the conductor. When the conductors carry the current in the opposite direction, then the closed part of the conductor carries the more current. Okay, effective resistance of the conductor is increased due to the proximity effect. So the resistance will be increases the proximity effect. Whenever you have to increase the proximity effect, so at that time the resistance value will be also increases. So factors. So now you have to see the factors affecting on the proximity effect. So what are the factors? Okay, so here the following factors. Okay, so the following factors affects the proximity effect. Okay, those frequency, diameter, structure, material. Okay, so when you have to take these parameters, okay, so these all factors will affecting the proximity effect. What the way, so these are affecting. Now we have to see frequency. See here, the proximity increases with increase in the frequency. Okay, so here the proximity effect will be increases with increase in frequency. Diameter. Similarly, the proximity effect increases with the increase in diameter of the conductor. So whenever the diameter will be increases, so at that time the proximity effect will be also increases. Similarly, same as skin effect. Skin effect is also increases with increase in frequency. Similarly, the proximity effect will be also increases with increase in frequency. Structure. So structure is also one of the factor to affecting on the proximity effect. The effect is more on the solid conductors as compared to the standard conductor. Okay. So coming to the structure of the solid conductor and standard conductor. So it is more on solid conductors compared to the ASCR. Okay, aluminum, silicon conductors. See, because of the surface area of the standard conductor is smaller than the solid conductor. Okay, the solid conductors having surface area is more, but the ASCR is the surface area will be less. Material. If the material is made up of high ferromagnetic material, then the proximity effect is more on their surface. So if suppose you have to take in the ferromagnetic material, so at that time the proximity effect is more on the surface. Okay, so these are the factors will affecting on the proximity effect. Okay, so these up to now we have discussing about the resistance and what is the resistance, what is the formula, and which factor will be resistance. So and which effect will increase as the resistance. What those are skin effect and proximity effect. So next, so and what are the factors? So and you have to see what is the skin effect, okay, and what is the proximity effect, and what are the factors will affecting the skin effect and proximity effect. Next, you have to see the inductance, line inductance. See, the current flow in the transmission line induces the magnetic flux. When the current line changes, the magnetic flux also varies due to the which EMF induced in the circuit. Okay. So line inductance is nothing but the current. So whenever the current will flows in the line induces the magnetic flux. Okay, whenever the current will flows through the transmission line, so at that time it produces the magnetic flux. When the current in the transmission line changes, so whenever the current value will be changes, the magnetic flux also varies. Okay, so at that time the magnetic flux also varies due to which EMF induced in the circuit. Okay, so see the magnitude of the induced EMF depends on the rate of change of flux. So at that time the magnitude of that inducing EMF depends on the rate of change of flux. Okay, see here EMF produced in this transmission line resists the flow of the current in the conductor. So what is the electromagnetic force produced in the transmission line will resist the flow in the, and this parameter is known as the inductor. Okay, so that EMF, okay, so that EMF will opposes that flow of current in the conductor. That parameter is known as the inductance of the line. Okay, see here the line inductance. Okay, here the line inductance can be calculated as L equal to flux linkages per unit current. Okay, so why you can why you can define the inductance means the flux linkages per unit current. You can say that is nothing but the line inductance. See here L equal to 5 by I Weber turns per ampere. Phi is nothing but flux linkages in Weber turns and I means current in amperes. Okay, so that's why here you can indicate 5 by I. Okay, so Weber turns per ampere. Okay, see here. Therefore, in order to find the line inductance of a circuit, the determination of the flux linkages is of the primary importance. Okay, so here whenever you have to find out the inductance value. Okay, inductance value, L value. So at that time, okay, so therefore in order to find the line inductance of a circuit, the determination of a flux linkages is of primary importance. Okay, it is important to first to find out the flux linkages. Okay, the total flux linkages of a circuit is equal to phi internal plus phi external. Okay, how you can calculate the flux linkages means here you have to take the flux linkages is sum of the internal flux linkages and external flux linkages. Okay, see here if changing current flowing through a coil produces flux linkages in the same coil, okay, then the flux linkages are called up internal flux linkages. So here what are the internal flux linkages and external flux linkages means If change in current flows through a coil produces, if suppose in one coil the current will flows, so that current value will be changes. Okay, that changing current value produces flux linkages. That flux linkages will be referred as the internal flux linkages. If suppose if changing current flowing through the coil produces flux linkages in another coil. Okay, that means if suppose if one coil the current will flows produces the flux linkages in the other coil, that flux linkages will be called as the external flux linkages. Okay, so here how you can calculate the flux linkages due to internal flux. Phi internal. Okay, so you have to find out the phi internal and phi external, and finally you have to add these two parameters. Okay, first of all, flux linkages due to internal flux. See here, let us consider a single conductor. If suppose you have to assume the single conductor in which current is flowing through is I. Okay, see here, you have to take in single conductor. In that one the current will flow through the conductor will be I. So to calculate the inductance, we need first to calculate the flux linkage of the conductor. So in previous we have to discussing to find out the inductance value. Firstly, you have to find out the which value flux linkages value. Okay, so okay, so the conductor, okay, so the conductor will produce a magnetic flux in it is surrounding due to its own current. Okay, so the conductor, so what is the conductor is produces magnetic flux, okay, that is surrounded by its own own current I. Okay, see here, let us assume a conductor radius R. Okay, here you have to take the one conductor, that conductor radius will be assumed R. Current I is supposed to be uniformly distributed over the entire cross section of the conductor. See here, you have to assume the radius of the conductor will be R. Okay, and here the current I will be uniformly distributed over the entire cross section of the conductor. Okay, see here, consider a differential strip. Okay, so here consider a differential strip thickness dx, differential strip of thickness dx at the distance x from the center of the conductor. Okay, see here from the center of the conductor, here you have to assume a differential strip length having dx. Okay, so as shown in figure, let the current flowing through the conductor radius x is the ix. So through that only x radius, here you have to assume ix. That value will be given as I into pi x square by pi r square. Okay, so that means the radius of pi through x cross sectional and radius of r. So at that time I of x square by r square. Okay, so see here, magnetic field intensity due to this current is. So magnetic field intensity is given by Hx equal to. So magnetic field intensity is denoted with H. Hs equal to Ix by 2 pi x. So this value is substitute. Okay, so but in previous you have to get the Ix equal to I of x square by r square. So that value will be substitute in this equation. So at that time okay, assuming the permeability of the conductor be mu. Okay, so whenever you have to assume the permeability be mu, so magnetic flux density at the consider point x. So at the time the magnetic flux density is given by Bx equal to mu Hx. Okay, so here you have to substitute Hx value. So Ix by 2 pi x. Okay, so at that time here you have to substitute in this equation. So at that time the magnetic flux density in Bx is equal to mu Ix by 2 pi x Tesla. Okay, so in the magnetic field intensity is measured in ampere ton per meter, but the flux density value will be always measured in Tesla or Weber per meter square. Okay, so here now flux flow assumed cylindrical shell of thickness dx and axial length L given as So here you have to assume that thickness will be dx and axial length L. So at the time d phi x equal to bx dx. So here bx means here you have to write mu ix by 2 pi x and dx Webers. Okay. So for air mu equal to mu naught. So actually mu equal to mu naught into mu r. So that means permeability equal to absolute permeability into relative permeability. Mu equal to mu naught into mu r. So whenever you have to take the free space in air, mu r value will be always 1. So at that time mu is directly equal to mu naught. So at that time you have to substitute in this equation. So in place of mu you have to substitute mu x. So bx d phi x equal to bx dx. Okay. So mu naught ix dx by 2 pi x. Okay. So now you have to substitute this one in the equation number 1. So in the place of ix, you have to substitute from equation number 1, I of x square by r square in this equation. Okay, so now at that time finally you can get d phi x equal to mu I x by 2 pi r square dx. Okay, see here the flux linkages per unit length of the conductor is given by, okay, so flux linkages. So for particular area, here you can explain, you can define per unit length. So at that time you have to write d lambda. Flux linkages are denoted with lambda r. So at that time pi x square by pi r square d phi r. Okay. So here in the d phi x. So in the place of d phi x, here you have to substitute this one. Okay. So by all you have to evaluate. Finally you can get d lambda r equal to mu I by 2 pi r to the power of 4 into x square dx. Okay, therefore the flux linkages for a single conductor due to internal flux found by integrating from 0 to r. Okay, so due to internal flux from 0 to r, so lambda internal equal to integral of 0 to r. Here you can get mu I by 2 pi r to the power of 4 x cube dx. So finally you can derive that, you can calculate from this formula lambda internal. Finally you can get the lambda internal equal to mu I by 8 pi Weber per tons. Okay, this is the internal flux. Now you have to find out the external flux. Okay, flux linkages due to the external flux. Okay, see here, now you will calculate the flux linkages of the conductor due to external flux. Okay, so the external flux is also created by the own current of the conductor. Okay, so and extends from the surface to the infinity. Okay, so internal flux means only internal into the conductor, but here the external flux will be the external flux also created by the own current of the conductor and extends from the surface of the conductor to the infinity. Okay, see here, let us again consider a cylindrical shell of radius x and thickness dx as shown in figure. Same as, okay, x, okay, cylindrical differential length dx, same as previous one. So now here you have to calculate again the internal external flux. Okay, see here, the magnetic field intensity at the surface of the cylindrical shell is given by h equal to I by 2 pi x. Okay. So that means current I is carried by the conductor. Okay, magnetic flux density, you have to know B equal to mu h. H place, here you have to write I by 2 pi x. So at the time the formula will becomes B equal to mu I by 2 pi x. Okay, so therefore the flux considered in cylindrical shell. Cylindrical shell you have to take in the d phi equal to B dx. Okay, so at the time in the place of B, here you have to substitute equation number 3. Okay, so that means in the place of B, here you have to substitute the mu I by 2 pi x. Okay, so at that time whenever you have to substitute B equal to mu I by 2 pi x, so at that time the phi external equal to mu I dx 2 pi x Webers. Okay, and so this is the external flux. Okay, so the external flux is the infinity surface, then okay, d lambda equal to phi external. Okay, so then d lambda external equal to mu I dx by 2 pi x. Okay, so what is the formula? You can get the d phi external. Here you have to write mu I dx by 2 pi x. Okay, so here see the flux linkages of the conductor from the surface to infinity. Okay, from the surface to infinity you have to calculate phi external equal to r to infinity. So those are initial to some particular radius r. That is nothing but the internal flux linkages. But here the external flux linkages is goes for the infinity. So that's why here you have to write the phi external is equal to integral of r to infinity mu naught I by 2 pi x dx Weber per turns. This is the external flux linkages. Therefore, if you want the total flux linkages of the conductor, we have to write the internal flux linkages plus external flux linkages. Okay, so that is nothing but phi equal to phi internal plus phi external. So in phi internal, so phi internal you can calculate in the previous formula is nothing but mu naught I by 8 pi plus integral. So this one is phi external is integral of r to infinity mu naught I by 2 pi x dx. So from these two terms, okay, from these two terms you have to common the mu naught I. Here also 2, here also mu naught I by 2 pi. So whenever you have to calculate, whenever you have to common the mu naught I by 2 pi, so at that time here you have to write the no term 1 by 4 plus integral of r to infinity dx by x. So units are Weber per tons per meter length. Okay, so this is the total flux linkages of a conductor. Why you are calculate these flux linkages means to find out the inductance. So to find out the inductance value, we have to find out the flux linkages by current. Okay, you want the flux linkages through the one conductor, you have the internal flux linkages and external flux linkages. So at the time you have to separately find out the internal flux linkages and the external flux linkages, and finally you can add these two flux linkages. At the time you can get the total flux linkages. Okay, so in this class we have discussing about the transmission line parameters, those are resistance and inductance. Okay, in next class we have to discuss the capacitance. Okay, thank you.